started. Answer your names, please. Emil. Lassie is here. Bishop. Here. Brad. Here. Odell.
Here.
Chestnut. Coolwood. Here. Erlinson. Here. Gerard. Green. Kennedy. Leonard. Mohammed Boy is here. Small. Solomon. Here. And the Swiss duck. All right, so we're going to continue from where we left off the last time. And if I remember correctly, we already did this problem, right? Did we? Yeah. If I recall? Yeah. All right. So we're going to do this problem where you're given this block of wood, you're given the dimensions, and the question is asking what would be the volume in cubic centimeters, right? Let me see if I can squeeze the answer beside it. Oh, you know what? Let me move this to the side, and I'll do the answer beside it. All right. So, of course, by now you all, based on your previous math experience, know how to calculate the volume of an object like this. Volume would be equal to the length times the width times the height, right? So that would be in this case 4.41 inches times 4.13 inches times 7.36 inches, right? So basically, if you were to do this calculation directly, your final answer would be expressed in inches cubed because you're multiplying the inch units across as indicated here, right? However, the question is not asking for the answer in inch cubed. It's asking for the answer in centimeters cubed, or cubic centimeters. So what that would mean is that it would be necessary for you to multiply this by a conversion factor. So if you go to the tables, you'll see that the relationship between the inch unit is that 1 inch is equal to 2.54 centimeters, right? So because you have inches here, along here, I'm going to put a 1 inch down here. But up here, I'm going to put 2.54 centimeters. So I'm just going to put an arrow here, 2.54 centimeters, right? However, because you have inch multiplied by inch here, that means you have to cube this conversion factor so that this inch unit will be cubed and will cancel out with each of these inch units here, here, and here. So therefore, basically, you're just going to do the arithmetic, but you have to make sure that the 2.54 centimeter is cubed when you're doing the calculation. So we're going to multiply 4.41 by 4.13 times 7.36 times 2.54, and this would have to be cubed. And when rounded out to 3 sig figs, the answer I got is 2.20 times 10 to the 3, and the units here would be centimeters cubed as required. And that's basically how that is done. All right? Any questions about this? Any questions? Any questions? Questions? All right, moving along. So here's another example. Again, involving conversion of units. So the question talks about the body mass index. I don't know if you're familiar with that measurement. It is used as somehow a measure, and I've been told not too accurately, of your overall health based on your mass and your height. So basically, to measure BMI, as stated here, it is a mass expressed in kilograms divided by the square of the height of the person in meters, all right? And therefore, as a result, the units of BMI is kilograms per meter squared. So they're saying, for example, if the BMI exceeds 25, then the person is considered to be overweight. So the question is asking here, what is the BMI of a person who is 69.0 inches tall and weighs 158 pounds? So as we said before, BMI would be equal to the mass divided by the height squared, right? So the mass of this person is 158 pounds, and the height is 69.0 inches, all right? So basically, we need to convert this to kilograms per meter squared. So what we have to do is focus on each of these values, convert the pounds to kilograms, and this should be squared, by the way, this should be squared. Yeah, all right. So basically, you're going to convert the pounds to kilograms and the inches to centimeters. Now, it doesn't matter which one you do first. I'm going to do the inches to centimeters first because I remember the relationship between those two units. And basically, you're going to have 1 inch above and 2.54 centimeters below. But because this value is squared, you have to square that, right? And then now to go from pounds to kilograms, no, that one I don't remember. I'd have to go to the table. So let me get over that and go to canvas, files. I should have had this up already. Tables, where are the tables? And chemistry, download. So basically, 1 kilogram is equal to 2.2046 pounds, right? So here I'm going to put down here 2.2046 pounds. And up here I'm going to put 1 kilogram. All right, and that's the setup. So basically, once you set it up, you should find it very convenient for you to cancel out the appropriate units. The inches squared and the pounds will cancel out, and you'll be left with kilograms. Oh, there's one more step. I'm sorry, because you want to go to meters, right? So one more conversion factor is needed where you convert, excuse me, centimeters to meters. That would be 100 centimeters is equal to 1 meter, and that would be squared. So basically, the centimeter units will cancel out. So the final units will be kilograms per meter squared. So all we have to do now is the number crunching, 158 divided by 69 squared. And then I'm going to multiply or divide by 2.54 squared, divide by 2.2046, and then multiply by 100 squared. And according to my calculation, this will be equal to 23.3 kilograms per meter squared. So this person, according to the standards, is not overweight, maybe close to, but not quite. All right? Okay, any questions about this exam? Any questions? Any questions? No questions? All right, so let me scroll down to the next slide. So let's talk about this property of density. I don't think we talked about it before, but density is also another physical property, one of the more quantitative ones. And by now, we should all know what density is. By definition, it's the mass of a substance divided by its volume. And as such, the unit of density is dependent on what units you use for the mass of the volume, right? So the mathematical formula for that density calculation is given right there. So therefore, the mass is in kilograms, or I should say, the mass is in grams, and the volume is, let's say, in centimeters cubed, then the density would be in grams per cm cubed. And usually, the density of liquids and solids are normally expressed in grams per cm cubed. However, in the case of gases, because gases occupy a larger volume compared to solids and liquids for the same mass, then we typically express the density of gases in grams per liter, all right? And the thing about gases and densities that we cannot use directly, at least, the density of a gas as one of those defining characteristics, because as you're going to learn, or you should have learned in your introductory chemistry, gases, their volumes vary drastically according to different conditions, like temperature and pressure. So because the volumes vary drastically for the same mass, we don't use density as one of those identifying characteristics of gases, but we do use density for identifying solids and liquids because their volumes do not change drastically when the temperature changes. So an example, of course, here shown of the density of a liquid is 0.791 grams per mil, and that's methanol, right? And as stated here, the density can be expressed as a conversion factor, right? You can express it either in this way or this way, depending on the type of calculation you're trying to achieve, all right? So let's look at a couple of examples right here. The first one says, a beaker has a mass of 85.2 grams when empty, and then 342.4 grams when it contains 325 mils of methanol. What is the density? Well, this one is a straightforward one. If you recognize that, of course, the mass of the liquid would be the difference between these two. So therefore, the density would be equal to the mass of the liquid, which is 342.4 grams minus 85.2 grams, and then we divide that by the volume, which is 325 mils. And then we work that out. So we work out the top part first, the numerator, 342.4 minus 85.2. And according to my calculation, this works out to be equal to 157.2 grams still over 325 mils. 25, right? So now we're going to divide that by 325. In this case, we have to round off to 366. So according to my calculation, this works out to be 0.791 grams per mil, which is the density of the methanol that we saw earlier, right? So that's a relatively simple example. Any questions about that? Any questions? Let's look at the next one. Now, the next one, they're asking for the mass of methanol in kilograms, right? They gave you the volume, and that's it. That's all they gave you, and they're asking for, well, you're going to need the density, right? So this number that we just used for determine is what we're going to use here. So basically, we know that density is equal to mass over volume. So therefore, to find mass, that will be equal to density times volume. The density is, as we saw before, 0.791 grams per mil, while the volume is given as 15.5 gallons. Now, obviously, we cannot just simply stop there because the gallon units will not cancel with the mil units. And the question is asking for the mass in kilograms, right? So we have to do some unit conversion. First one I will do, and it doesn't matter the order of the units conversion. The first one I'm going to do is I'm going to convert from grams to kilograms. So we know that 1,000 grams is equal to 1 kilograms. So the way I'm going to express this here is that I'm going to put 1,000 grams down here as a denominator and 1 kilogram up here as a numerator. Now the next conversion factor is to convert the milliliters to gallons. And again, I don't know what the conversion factor is, so I have to consult the table. So let's see here. According to this, where is it? Where is it? Okay, so according to this, 1 gallon is equal to 3.7854 liters, 3.7854 liters. So I'm gonna put, well, right, it's gonna be before, 1 gallon is equal to 3.7854 liters. Right, so the first thing I'm gonna do is, in order to get that conversion going, is to convert from milliliters to liters. So I'm gonna put 1,000 mils above and 1 liter below. And then the next conversion factor, I'm just gonna continue down here, would be the conversion of the liters to gallons, as I said up here. 1 liter is equal to 3.7854 gallons. Oh, I'm sorry.
That's exactly.
Should be the other way around. Okay. Well, it should be 3.78 854 liters and 1 gallon below, all right? So again, the setup is such that, you know, the units you want to eliminate will be eliminated, like the gallons will go, I'm sorry, milliliters will go here and here, the liters will go here and here, and what else? The gallons will go here and here, and grams will go here and here. So the final answer will be expressed in kilograms, which is what the question is asking for. So again, we have to do the number crunching, 0.791 times 15.5 divided by 1,000 times 1,000, so they'll cancel out. And then times 3.7854. So according to my calculations, rounded off to 3 sig figs. And again, please correct me if I'm wrong, but I got 46.4 kilograms. That's how that is done. All right. Any questions about this one? Any questions? Okay, so also you guys out there in Zoom, please feel free to chime in if you have any questions. All right, so I think that's it. Yeah, that's it for this chapter. So based on what we have covered, you should now be able to do, let me go back to assignment number 1. And let me see here what is it. Okay, so this is assignment number 1. Yes, sir.
What was the answer to the last problem?
46.4. Okay, let's see here. So I don't think we have done. Have we done this one? Assignment 1?
We haven't worked through it.
Huh?
We haven't worked through it in here.
Okay, all right. So let's go through this one then. This question says a star is estimated. Yeah, we'll put that down because this is a density question. It says a star is estimated to have a mass of 2.0 times 10 to the 36 kilograms, assuming it will be a sphere with an average radius of 4.96 times 10 to the 5 kilometers. Calculate. First question is asking for you to calculate the mass of the star in milligrams. So in this question here, you're going from the mass expressed in kilograms to milligrams. So in order for us to do that, you'd have to first convert from kilograms to grams and then from grams to milligrams, right? So we're going to start off with the 2.0 times 10 to the 36 kilograms. And we're going to convert to grams. So we're going to have 1 kilogram down here, 1,000 grams above. Kilogram units will go, and then we do the conversion from grams to milligrams, which means that you're going to have 1 gram down here, 1,000 milligrams above. No, Delaware Road, keep messing. It's going to be 1 gram below, 1 gram below, and 1,000 milligrams above. So the gram units will cancel out. So when you do that calculation, going to according to my calculation, 2.0 times 10 to the 42 milligrams, right? So that would be the density, I meant not density, I'm sorry, the mass of the star. All right, any questions about this? Questions? Questions? All right, so it's okay for me to clear this? Yeah, you just put it into your calculator. And let me just say this, I think I told my introductory group this before. You have to be careful when inputting your number expressed in scientific notation on your calculator. And to be frankly, it is dependent on the brand, or even within the same brand, the type of calculator, all right? There are different ways in different calculators to express, like for example, 2.0 times 10 to the 36. That's very important because one common error that students tend to make is that, for example, when they're typing in 2.0 times 10 to the 36, they literally type 2.0 multiplication sign 10 raised to the 36, right? Problem with that is that when it comes to more complex type of calculation, just entering it that way will give you the wrong answer when you get your final answer. So the safest way to go about doing it is finding out how your calculator express a number in scientific notation like this. So for example, on my cheap Casio FX 250 or 260 Solar 2, I would have to enter 2.0, and then there's an EXP button right here, and it looks like this on my calculator. 2.0, and then you're going to see 2 zeros appearing here, and then you enter the exponent, which is a 36, and those zeros will be replaced by 36. So on my calculator display, this is the same thing as 2.0 times 10 to the 36, but that's my calculator, right? You have to figure out on your calculator how to express that. In fact, let me see your calculator. So like, for example, in this calculator here, oh, okay, so in your case, if you were to express 2.0 times 10 to the 36, it would be 2.0. And then in your case, a bit more complex because you have to go second function. And then you see that WE, and then 36. And that's 2.0 times 10 to the 36. So and this, if you happen to have this calculator, this is the TI-84 plus C Python. So it's dangerous. So it depends on your brand, and even within the same brand, I've noticed, like for example, mine is a Casio, but in other Casio calculators, I see they do. You have to do something different in order to express the number correctly in scientific notation. So, if you have any doubts about that using your calculator for that purpose, you can show me, but I can't guarantee you that I'll be able to help you because I've seen some calculators where I don't have a clue, right? So I will help as far as I can, but maybe what you should do is read the book that comes with the calculator to figure out how to express numbers like these in scientific notation. Okay, all right, so let me clear this. And let me scroll down. Okay, so this one says the volume of the star in kilometers cubed, and they gave you the formula for calculating the volume of the star right here, right? So what was the radius? 6.96 times 10 to the 5. So the volume will be equal to 4/3 pi 6.95 times 10 to the, just to make sure again. 6.96 times 10 to the 5. Okay, so 6.96 times 10 to the 5 kilometers cubed. All right, and that's it. So let's see what is here. So 6.95, oops, 6.95 times 10 to the 5, and then cube it and then times pi. And then times 4 divided by 3. Okay, so this is what I got, rounded up to 3 sig figs, 1.41 times 10 to the 18 kilometers cubed. All right, so that would be the volume of the star in kilometers cubed. And then the question is asking in the C part, the density of the star in milligram per kilometers cubed, right? So density, of course, equal to mass over volume. What was the mass we got before the A part? And somebody remind me,
20 times, or 2.0 times 10 to the 42.
2.0 times 10 to the 42. That would be in milligrams divided by the volume that we just determined here. 10 to the 18 kilometers cubed. So let's see what that gives. 2 times 10 to the 42 divided by 1.41 times 10 to the 18. And according to my calculator, now this you have to round up to 2 sig figs. So 1.4 times 10 to the 24 milligrams per kilometers cubed. That would be the answer for the C bar. All right. Any questions about either B or C? Questions? Okay. So let me clear this. And let me scroll down. Okay, did you do this one already? I think you did this one, right? Yeah. Okay. I remember doing it. Okay, I don't think we have done this one. Okay, so they gave you the length in centimeters, and they're asking for the equivalent length in inches. So based on what we have just learned, how would you go about doing this problem?
Divide 45.6 by 2.
All right, let's set this up correctly, so 45.6 centimeters. And you said divide by what?
2.5.
2.54 centimeters. And up here you have 1 inch, right? So whenever you're doing this calculation, make sure you show the setup so that I can see that you're following the logic and the units will be canceling out that you need to get rid of and all that. So 45.6 divided by 2.54 and round it off to 3 sig figs, that would be equal to 18.0 inches. All right? Okay. That one is pretty simple. What about number 5? How would you go with this one? Let me start you off. We're going to start off with 1.23 times 10 to the minus 6 kilometers, right? So what would you multiply this by first thing? Remember the aim is to go from kilometers to centimeters. Okay, so what would you put up top and what would you put below here?
1 meter and 1,000.
1 meter above? Well, not 1 meter.
1,000.
1,000 meters actually. Because kilo means 1,000, right? So 1,000 meters will go above and 1 kilometer will go down here. So this goes to that. Then what? We need another conversion factor because we need to go to centimeters. So what would go up top? What would go below here?
1,000 centimeters.
1,000, sure? 100 centimeters is equal to 1 meter. So 1 meter down here, 100 centimeters above. So this goes with that. And then we do our number crunching. So according to my calculation, this works out to 0.123 centimeters. That's how we do that. Here, minus 6. Okay, any other question? Any other questions? All right, let me clear this. Let's keep going further to see if there's any other question. Oh, some more conversion. All right, very good. So how would you go about tackling this problem? They gave you 34, write this down, 34.5 years, and you asked for the equivalent value in hours. So what would be your first conversion factor here?
Days.
Hmm?
Days.
Okay, so you're assuming it's not a leap year, that would be what?
365.
1 year equal to 365 days, all right? Years will cancel out. What next?
1 day is right.
1 day is equal to 24 hours, all right? I can work with that. 365 times 24. Okay, now this would have to be rounded off to 3 sig figs. So the answer I got is 3.02 times 10 to the 5 years. That's what we do. All right, I'm sorry, hours, yeah. Thank you. Because this will cancel that, so hours will be that. Okay, any questions about this? Any questions? Okay, the next one, they gave you 355 millimeters. And you have to convert that to inches. So what do you think the first conversion factor would be?
Go millimeters, centimeters, probably.
Okay, so what goes up top, what goes below?
Centimeters on top, millimeters on the bottom.
And what would be the numbers?
There's 1,000 millimeters to 100 centimeters.
Okay, so that would be. Okay, it could be that way. I wasn't thinking along, but you're saying 100 centimeters would be equal to 1,000 millimeters,
Right?
right? I was thinking 1 to 10. It's the same, ratio, right? But just as correct. So the millimeters will cancel out here and here, but remember, we're aiming for inches. So what's the next conversion factor? And this one you may need to look up because I don't expect you to remember all of them.
1 inch.
1 inch goes where? Top, and what goes below here? 2.54 centimeters. So that goes with that. So let's see what that gives. 355. I'm just gonna say divide by 10, and then divide by 2.54. And according to my calculations, again, I could be wrong, but that's what I got. I got 14.0 inches. Right? Okay, any questions about this one? Any questions? Any questions? Okay, the last one on this, well, let me make sure it's the last one on this page. Oh, there's more, okay. Here's this. Okay, so. All right. Okay, so for number 8, it says how many milliliters are in a cubic meter? So basically, they're asking 1 meter cube, you're starting from that. Right, cubic meter is the same thing as 1 meter cube, right? And they're asking for how many milliliters are present in that 1 meter cube. And they give you a little hint here, or a little help. They're saying that there's 1,000 liters in 1 meter cube. Okay, so what would be the first conversion factor you would use in this case? What would go up top as the numerator and what would go below as the denominator?
Top 1,000 liters.
Okay, 1,000 liters and below 1 meter cube. Very good. That goes with that, right? And then remember now the aim is to get to milliliters, right? So how would you convert liters to milliliters? And again, you may refer to the tables where you deal with metric prefixes. If you can't remember off the top of your head. So what's the relationship between a liter unit and a milliliter unit?
10 milliliters.
Nope.
1,000 milliliters to a liter.
1,000 milliliters. will be equal to 1 liter, right? So that would go with that. So the final answer would be 1,000 times 1,000, that would be 10 to the 6 milliliters would be the answer. Right? That's how you do that. Okay. Any questions about that? Any questions? Okay, number 9, how many miles are there in 3.44 times 10 to the 8 inches, right? And they're giving you a little help here again. 0.61 miles in 1 kilometer. So you're starting off with 3.44 times 10 to the 8 inches. And my question to you is, what would you multiply this by first? What would be the conversion factor you would use first or in the first step? Hmm? I guess you could do that, but that would, you'd have to really delve into the table.
Centimeters.
Yeah, I would prefer to go that route. Not that what you're saying is wrong, right? And this is another important thing I probably should mention too. It is possible to go through different routes when it comes to questions like these, to take different, series of conversion factors, and you should get the same answer. Some situations will be more complicated than others. I like to do the simple or the simplest pathway. You tend to make less mistakes going that way. So I would go with what he's saying. Go from inches to centimeters. So what goes up top here, what goes below here? What's the relationship between the inch unit and the centimeter unit?
2.54%.
Right, so 2.54 centimeters will go up top. And 1 inch would go below, so the inch units will cancel. Okay, very good. What's the next conversion factor you would use? Remember, the aim is to get to miles, right? So we have converted successfully from inches to centimeters. What would you think the next step is? Okay, so how would you get from centimeters to kilometers? I would go to meters first. So what's the relationship between meter and centimeters? 100 centimeters equal to 1 meter. So how would you set that up here? What goes up here, what goes down here? 100 centimeters go below and 1 meter above, right? So that this goes in that. And then now, what do we do next? To get to kilometers, like you were suggesting. 1,000 meters down here. And 1 kilometer above, right? So that this goes with that. And then what? One more step, because remember, ultimately, we're trying to get to miles, right? So there's one more step. Hint, right here.
1 mile.
No, not 1 mile. 1 kilometer down here. And 0.61 miles here. See what I'm saying? So that this goes with that. So now we have to do the number crunching, 3.44 times 10 to the 8 times 2.54 divided by 100 divided by 1,000 times 0.61. And according to my calculation, now in this case here, I need to make the point that these numbers here, or the numbers involved here, are exact. The same is true here. The same is true here. But this one is not exact because this is a relationship between a metric and non-metric unit. So you have to round your answer off to 2 significant figures in this case. So that would be equal to, according to my calculator, 5.3 times 10 to the 3 miles, or 5,300 miles. 300. Right. Okay, any questions about this one? Number 9, any questions?
I ran it a little different way and
What did you get?
I came quite a bit different, 5,429 miles.
Not bad.
So I
As
did,
long as I would like to see later when we're through, but it is possible that your way is just as legitimate. This relationship between kilometers and miles is actually less accurate than what's in the table, right? So if you use the tables or if you use some other legitimate conversion factors or series of conversion factors, I would give full credit as long as that, it checks out.
I converted it to feet and then feet to
Okay.
miles.
Okay. And it's not far, what you just said is not far from the 5,300, I mean, by 100
129 miles.
miles, yeah. Okay. You got a question? Oh, okay, but yeah, I'd like to see what you did, but show me afterwards. Okay, any other question, any other questions? All right, let me clear this. Let me do this, scroll down, okay, now this one is interesting. It says a waterbed is filled with water and it has the dimension that you're given. And you're given the density of water. So the question is asking, determine the kilogram of water needed to fill the waterbed, right? So this is a density question, right? So we have to remind ourselves of the formula for density, which is density is equal to mass over volume, right? What the question is asking for is the mass. So that means that the mass is equal to the density multiplied by the volume, right? So basically, the volume, of course, can be calculated using the same formula that we used earlier. If you remember that block of wood example that we did, right? So it's the same thing that we're going to do when it comes to calculating the volumes or the volume of the bed. So, and they gave you the density, right? So in this case, the mass will be equal to the density, which is 1.00 grams per cm cube, multiplied by all this here, 8.0 feet times 7.0 feet times 0.75 feet, right? Now you'll notice, of course, that down here you have the volume expressed in centimeters cube, and the result of multiplying feet by feet by feet will give you feet cube, right? So we have to do some conversion here, right? And I would say the most convenient way of going about it is try to convert the feet units to centimeter units, or more specifically, feet cube to centimeters cube. But before we do that, we also need to convert the grams to kilograms, because the question is asking for the mass of water ultimately in kilograms. So what I'm going to do first is convert a gram to kilograms by 1 kilogram above, as enumerated in this conversion factor, and 1,000 grams below, right? So that this gram units will cancel out with that gram unit, right? Then we worry about now converting from feet to centimeters, right? So we know that feet can be converted to inches. So the way we set that up here is that we're going to put 12 inches above and 1 foot below. But because the result of multiplication here with the feet cube, we have to cube that. All right, so that this feet cube unit will cancel out with all of those. All right, and then now the next conversion factor is where we convert from inches cube to centimeters cube. And again, as we saw before, 1 inch is equal to 2.54 centimeters. And again, we have to cube that so that this inch cube unit will go with that inch cube unit. All right. So basically, oh, and also this centimeter cube unit will go with that centimeter cube unit. All right. So ultimately, the remaining unit will be kilograms, which is what the question is asking for. So all we have to do now is, again, do the calculation. So 8 times 7 times 0.75 times 1,2 cubed times 2.54 cubed. And then, okay, so this answer now has to be rounded off to 2 sig figs, because we have 2 sig figs here, here, and here. We have 3 here. This is exact, that's exact, that's exact. Okay, so when rounded off to 2 sig figs, I got 1.2 times 10 to the 6 kilograms. Again, please correct me if I'm wrong. if you have done the calculation yourself and you think I made a mistake somewhere, but this is what I have. Right? Any question about this? Any questions? Any questions? All right. Can I clear this? I can clear this. Okay, oh, this one is interesting. All right, so this question talks about having an oil slick, right? Where it spreads, the oil that is, spreads on the water and forms a layer which is 120 nanometers thick, right? So the question is asking, how many square kilometers of the ocean will be covered by the slick formed when 2 barrels are spilled, right? And it gives you the relationship between a barrel and gallons. 1 barrel is equal to 31.5 gallons, all right? So the key thing in this question is, what is the mathematical relationship between the area covered by the slick and the thickness of the slick, right? And you should have learned in whatever math course you may have completed before that there's a relationship between, if you think about, should I explain this? If you think about an object, it's not exactly the same thing as an oil slick, but let's say you have a rectangular object like this. And this could be true for any other regular shaped object, right? One way of calculating the volume is calculating the area here, right? So the volume would be equal to the area, and then the area, so this is the area, and this would be the height, which would be equivalent to the thickness times h, right? So this is one way of calculating the volume. Now, in this particular question, what the question is asking for is this, which would be equivalent to the thickness of the slick. So if we rearrange this equation, you're going to get h is equal to volume divided by area, right? Now they gave you the volume as 2 barrels. Continue down here. So h would be equal to 2 barrels. I'm just going to say BAR for barrels. Divided by the area. Let me see. Oh, I'm sorry, my bad. The question is not asking for the thickness. They gave you the thickness. The question is asking for the area. So I need to switch those two. So I'm going to put the area here and the thickness here, right? So the thickness is 120 nanometers. All right? So basically, this is what we have to work with. However, the question is asking for the square kilometers, right? For the area. So somehow we have to do some conversions in order to get the final answer in kilometers squared. So they kind of help you out a bit here because they gave you the relationship between the gallons and the barrel. 1 barrel is equal to 31.5 gallons. So the first thing I'm going to do here is put 31.5 gallons above and 1 barrel below, right? So that goes with that, right? And then ultimately, and let me just give you an overall description of what you're trying to achieve. Ultimately, you want to get the volume expressed in kilometers cubed, and you want to get the thickness expressed in kilometers. So that when you divide kilometers cubed by kilometers, you're going to get kilometers squared, which is what the question is asking for, right? So basically, you want to convert the volume to kilometers cubed, and you want to convert the thickness to kilometers. So continuing with this here, so here I really need to refer to 2. So let me go to the, where's it here? Oh, okay. Okay, so how would I go from this here? Gallons to kilometers cubed. Okay, so we can say, we see here that 1 gallon is equal to 3.7854 liters. So I'm going to put here 1 gallon below and 3.7854 liters, right? And then we can go from liters to centimeters cube. Okay. So we can go from liters to centimeters cube. And that would be 1,000 centimeters cube divided by 1 liter. Okay, so far this will cancel with that will cancel with that, and then we can go from centimeters cube to meters cube, where one meter is equal to 100 centimeters. We have to cube that because you want the centimeters cube to cancel out. And then we can go from meters to kilometers. And that would be 1,000 meters down here and 1 kilometer above. Again, you have to cube that so that this meter cube will cancel with that meter cube. And then we have to convert from, oh, this is going to be a long, okay, let me see if I can squeeze at least one conversion factor here. We have to convert from nanometers to kilometers. So nano means 10 to the minus 9, by the way, if you look it up. So therefore we can put 1 nanometer here and 10 to the minus 9 meters here. And then I'm just going to continue down here. The last conversion factor is to convert the meters here. Oops. Convert the meters to kilometers. And of course, that would be 1,000 kilometers, 1,000 meters. So I'm going to put 1,000 meter down here and 1 kilometer below that. All right, so that this meter unit will cancel with that. This nanometer will cancel with that. And what's going to happen here is that this kilometers cube, one of the kilometers here will be canceled out by one of those kilometers. So the final answer will be expressed in kilometers squared. So let me see what that gives. 2 divided by 120 times 31.5 times 3.7854 times 1,000 divided by 100 cubed divided by 1,000 cubed and then divided by 10 to the minus 9 and then times 1,000 and according, oh, this can't be right. I did something wrong. I think inputting the numbers in my calculator. Let me try this again. 2 divided by 120 times 31. Oops. 2 divided. Times 31.5 times 3.7854 times 1,000.
1,000 cubed.
Hmm?
Is it 1,000 cubed?
No, you mean this one right here? That's not cubed. But this here will be cubed. So I'm going to divide by 100 cubed. And then I'm going to divide by 1,000 cubed in the next conversion factor. And then I'm going to divide by 1 times 10 to the minus 9. And then I'm going to multiply by 1,000. And this looks more correct. So the answer I got is And I have to round down to 2.6. So the answer I got here is 2.0 kilometers squared. Right, yes, sir.
What are the last two steps of the conversion?
Okay, yeah, the last two steps here is 1 nanometer divided by 10 to the minus 9 meters. Because nano means 10 to the minus 9. And then for this one, it's 1,000 meters divided by 1 kilometer. That's how that works out, all right? Okay, any other questions about this one? I think this is the last question, right? Is it?
Yes.
Okay, all right, so now that we have completed this, you need to submit this, online. Let me, well, firstly, can I clear this? All right, so let me do that now. And, what I'm gonna do is set up a Dropbox for you to submit your first assignment, so I'm gonna go to assignments. Okay, so for assignment 1. Okay, so let me go to 2025. And today is the 16th, so I will say that I'm going to make it due on the 20th, right? Go here. So it's available from today until the 20th. So basically what you're gonna do is scan your answers, your document, and make sure, I'm going to give you some rules for submitting assignments online. I'm going to post it later on today. So you're going to upload it into Canvas, make sure it's in the form of a PDF document, all right? Not PNG and not JPEG, right? And there's some other things you need to do. I won't go into it right now. I'll just post it in the announcement section, all right? So that's the assignment. Now, let's see. I want to start chapter 2 briefly, just to get you started on that. And then we'll call it today. We have 15 minutes left, so. Let me go here. And again, these are topics that you would have encountered already in your previous chemistry experience. And again, I'm going to try to go through it as quickly as possible as far as chapter 2 is concerned. Chapter 2, as you can see from the title, is dealing with atoms, molecules, and ions. All stuff that you should be familiar with. So let me just start by talking about different laws that govern chemical combination. The first of which is the law of conservation of mass, which says that the total mass remains constant during a chemical reaction. Another way of stating this is that matter is not created nor destroyed in a chemical process, right? In other words, whatever the mass of the products you end up with would be equal to the total mass of the reactants that you started off, all right? And then there's another law known as the law of definite proportions. And there are a couple of ways of stating this, but basically what they're saying is that all samples of a particular compound have the same composition, right? So for example, in the case of water, water is approximately 89% oxygen, and the rest 11% is hydrogen, all right? And that is true for every sample of water, regardless of where you get the water from, all right? And that is true for all compounds. They all have definite proportions. This is another example demonstrating this whole idea of definite proportions. I'm not sure what the substance is, but they gave us a breakdown as to the composition. It is 57.48% copper, 5.43% carbon, 0.91% hydrogen, and the rest is oxygen. And basically, it doesn't matter where you get this compound from. I think it's basic calcium, not calcium, basic copper carbonate, if I'm not mistaken. So it doesn't matter where you get a compound from, if it's the same compound, the composition would be constant for each substance or element present. Yes, it's basic copper carbonate, right? Okay, so let's look at this example. It says the mass ratio of oxygen to magnesium in the compound, the magnesium oxide is, I think gives you a ratio. The question is asking what mass of magnesium oxide will form when 2.000 grams of magnesium is completely converted to magnesium oxide by burning in pure oxygen gas. So that, okay, I guess this. All right, must be away from changing the color. Let me do this in the time that we have left. Let me get over this here. Let me, copy this. And, so this is the question here. Oh, no, what did I do? Oh, I copied wrong. This is what I did. Okay, so this is the question here. It says the mass ratio of oxygen to magnesium in a compound is the ratio. And the question is asking what mass of magnesium oxide will form when 2.00 grams of magnesium is completely converted to magnesium oxide by burning in pure oxygen. So what I would do first is find out how much oxygen has been incorporated in the magnesium. And where I would do that is I would take 2.000 grams of the magnesium and I would multiply it by the ratio that is given here, because this gives the ratio of oxygen to magnesium. So the oxygen part will go up here, 0.6583 grams of oxygen, and down here I'm going to have 1 gram of magnesium. So when we do the calculation, 0.6583, I got rounded off to 466, 1.257 grams, right? So that represents the grams of oxygen. So therefore, the question is asking, what's the total mass of the magnesium oxide? Total mass of MgO. The answer would be the 2.00 grams plus the 1.257 grams, and that would equal to 3.257 grams. But that's basically it. Right? That's basically how that question will be done. All right. Okay. Any questions about this one? Any questions? Any questions? Okay. So the next thing we're going to talk about is the law of multiple proportions. Now, this law is pretty wordy, many words involved. Let me just read it for you. It says when two or more elements different compounds of the same two elements are compared, the masses of one element that combine with the fixed mass of the second element are in the ratio of small whole numbers, all right? So let me try to illustrate what this law is actually saying. So let's say we're going to compare two compounds which contains the same two elements, but their proportions are different. One is carbon dioxide, the other one is carbon monoxide, right? So let's say we can set up an experiment where we start off with the same masses of carbon to react with oxygen to form the respective compounds. In one case, carbon monoxide, in the other case, carbon dioxide, right? So what you'll find if you do the relative or the respective measurements, what you'll find is that in the formation of carbon monoxide, 3 grams of carbon will react with 4 grams of oxygen. In the formation of carbon dioxide, 3 grams of carbon, the same mass as over here, will react with 8 grams of oxygen, right? So one can see that there's a relationship between the masses of oxygen that will react with the same mass of carbon, right? There's a 2-to-1 ratio, and that is basically what is calculated down here. And that is basically what this law is saying. What this law is saying is that if you have two substances made up of the same two elements, but the mass of one element is fixed, then the ratio of the other elements would be some small whole number ratio, right? In this case, a 2-to-1 ratio, all right? I think I have another example here. In the case of oxide of nitrogen that can be formed by combining with 28 grams of nitrogen, right? What you'll find is that in one particular case, 28 grams of nitrogen will react with 16 grams of oxygen. In another case, it will react with 48 grams of oxygen for the same mass. In another case, it's going to react with 64 grams of oxygen for the same mass. And for the fourth and final case, it's going to react with 80 grams of oxygen for the same mass of nitrogen. So again, you can see, if you closely examine these numbers here, you can see that we can basically express them as small whole number ratios, right? All you have to do is divide right through by 16, and you're going to get the ratio being 1. Oops. Oh, I forget, can't see. Or maybe you can't see here. 1 to 4 to 8. No, not 4, not 8, 4. No, what am I saying? This should be 3, sorry. So 1 to 3 to 4 to 5, right? So 1 to 3 to 4 to 5, that's the ratio of the masses of oxygen that will combine with the same mass of nitrogen, 28 grams, to give different compounds. And if you look at the formulas for these different compounds, you can see why this happens. So these are the compounds, right? And basically, as I said before, it's a 1 to 3 to 4 to 5. If you look at each of these compounds, for the same number of nitrogen atoms present, it's a 1 to 3 to 4 to 5 ratio between the oxygens that will combine with the same mass of nitrogen. So that's basically what the law of multiple proportions is all about. Okay, then we get to Dalton's atomic theory. Okay, let me go through the theory quickly. Again, this is something that you should have read before. So this guy, he was an English school teacher by the name of Dalton. In 1803, he basically came up with a theory based on what was known about substances, chemicals, how they behave. Back then, you know, people believed that atoms existed based on information that was provided or experiments that were done, and the results basically support this notion that, okay, the smallest unit that can exist in a substance would be an atom. So Dalton pulled all these ideas together, and he came up with some principal assumptions concerning how atoms behave and how they can explain, you know, what we observe as far as chemical reactions is concerned. So the first assumption made is that, according to his theory, is that matter is composed of atoms, which are tiny and indivisible particles. And let me stick a pin here and say that we now know that not to be true, right? We know that atoms can actually be broken down into smaller fundamental particles. If you get right down to it, they can be broken down into the 3 fundamental particles, which are the protons, neutrons, and electrons, right? Which is something that I'm quite sure you're all familiar with. Back then, he didn't know that, right? Folks back then involved in chemistry didn't know about the fact that you can actually break down the atom into smaller particles. So that's the reason why he said that, according to his theory, that the atoms are indivisible. All atoms of a given element are the same, well, we all know that to be true. Atoms of one element differ from atoms of other elements, we know that to be true as well. Compounds are formed when atoms of different elements unite in fixed proportions, that is also true, we know that to be true. A chemical reaction involves rearrangement of atoms, no atoms are created, destroyed, or broken apart. We know that to be true as well, all right? So that's basically Dalton's atomic theory. So just to see this example as a demonstration of that, we're looking here at the reaction between hydrogen and fluorine. The equation for this reaction would be H2 plus F2 to give HF, right? So based on this equation, two molecules of hydrogen fluoride will be formed from one molecule of hydrogen and one molecule of fluorine, right? So in this particular case, we have 6 fluorine atoms or 3 fluorine molecules, and here we have 2 hydrogen molecules. So basically, and we're going to talk about limiting reactant concept later on, but basically what will happen is that because hydrogen is limiting, it will react completely with 2 of these molecules of fluorine to form 4 molecules of hydrogen fluoride, but there will be 1 unreacted fluorine molecule, right? In any case, what you see here is that the total atom count for each element will be the same on both sides, right? So therefore, the atoms are conserved, which means that the mass is conserved, which basically falls in line with the law that we talked about, the law of conservation of mass that we talked about earlier, right? So basically, this is where the atomic theory is demonstrated to show that the theory or the law of conservation of mass works. All right, I think I'm going to stop here for today, and we're going to continue our discussion. So remember to submit that assignment by the deadline. And also, you may have seen the announcement I posted this morning. I won't be here for office hours, unfortunately. I must apologize for that. Instead, I'll be at Ocala. I'll still be available online. So if you have any questions, you can talk to me via Skype, or if you're going to be there, you can talk to me wherever you're. Yes, sir.
Could you possibly go back to the problem?
Which problem?
So, it's hard to tell you one.
Hold on, 1 minute. Part field number 2. Okay, here, yeah. What about it?
Oh, it's a work.
No, I have to erase the word. Well, basically for that one, I divide the mass that we got in A part by the volume in B part, and that gives you the answer. Right, because in the A part, hold on, I mean, in the A part, we calculated the mass of the star in kilograms. In the B part, we calculated the volume in kilometers cubed. So for the C part, you're dividing the A value by the B value. And that's it. Yeah. Yeah, let's see your approach. Where is it? Which one? Okay, so we start with inches. Okay, so the way I would yeah, set it up. It looks correct. This will be inches. Make sure you include the units. So this will be inches, right? And then it's 12 inches per foot. So 12 inches per feet or per foot. And then this will be
5,280
feet per mile. And what I will do is round this off to 3 6 things. So your answer actually should be 5,400. That's it. Which I'll give, you know, based on your setup, I'll give, well, make sure you include the units. Units are part of the process.
Okay.
But yeah, the setup seems legitimate, so. Alrighty, so let me, And for you guys out there in Zoom, I'm going to sign off right now.